A banana is not a static object. Once severed from its plant, it becomes a highly reactive biological system racing towards its own destruction. It belongs to a category known as climacteric fruit. For these crops, the physical act of harvest acts as a strict biological trigger, initiating an irreversible, accelerated aging process. Look at this graph tracking a banana's internal chemistry post-harvest. The baseline sets flat until it sharply spikes. Two distinct metrics surge simultaneously: its respiration rate, consuming oxygen to break down starches, and its production of endogenous ethylene gas, forcing the tissue to ripen. This dual biological spike establishes a strict countdown. Without immediate aggressive intervention, the fruit will consume itself during long-haul transit across the ocean. The central logistical challenge is managing millions of these actively degrading assets, moving them thousands of miles before that biological window closes. Global banana logistics is an active, continuous war against the fruit's own biological clock. Winning this logistical war requires two distinct, diametrically opposed phases of atmospheric engineering. Phase 1 relies on strict biological preservation. The goal is to completely suspend the climacteric clock while the cargo sits in oceanic transit. Phase 2 shifts to on-demand accelerated ripening, a chemical trigger applied exactly when the fruit arrives at the destination retail market. We will first map the standard preservation parameters that get the fruit across the ocean, and then deconstruct a patented, counterintuitive high-temperature ripening protocol used upon arrival. Manipulating the atmosphere around the fruit actively determines its final cellular structure and sweetness. Phase 1 begins with a rigid thermal threshold. The core pulp temperature must be dropped to a precise window between 13 and 14 degrees Celsius. If the ambient temperature climbs above 14 degrees, it triggers an irreversible climacteric ripening cycle mid-voyage. The cargo will spoil before reaching land. If the temperature dips below 12.8 degrees Celsius, the fruit suffers severe chilling injury. The extreme cold causes cellular death. Severe chill or physical shock ruptures cell walls, releasing an enzyme called polyphenol oxidase. It bleeds into surrounding tissue, permanently staining and ruining the pulp. Temperature control alone is insufficient. The industry relies on a secondary suppression mechanism utilized deep inside the shipping boxes, modified atmosphere packaging, or MAP. In the Banavac system, a tightly sealed polyethylene liner encases the fruit inside the cardboard box. This barrier restricts airflow, trapping respiration gases. The plastic film is engineered to raise carbon dioxide to 5% and drop oxygen to exactly 2%. Under these exact atmospheric conditions, the fruit's respiration rate is suppressed to its absolute minimum physiological limit. This precise combination of MAP gas control and thermal suppression effectively pauses the fruit's biological aging, keeping it viable for up to 40 days. Once the cargo arrives at the destination ripening depots, the logistical goal abruptly flips from absolute preservation to rapid, uniform acceleration. The standard industry protocol to trigger ripening is straightforward. Warm the holding room to 60 degrees Fahrenheit and flood the space with synthetic ethylene gas. Agricultural science maintained a strict ceiling on that heat. Operators assumed that elevating ripening temperatures further would cause premature starch-to-sugar conversion, yielding unmarketable, mushy fruit. U.S. Patent 2014-0072-682A1 details a counterintuitive ripening protocol that dismantles that standard industry logic. Unlike the standard 60-degree protocol, the patented method intentionally spikes the temperature to 75 degrees for green, color stage 1 bananas. Simultaneously, the room is flooded with a dense concentration of ethylene gas. This extreme pulse is restricted to a strict 24-hour window. By all standard post-harvest metrics, applying this extreme thermal and chemical load constitutes a biological paradox that should completely destroy the fruit's commercial viability. The consequence of that heat pulse is a massive internal reaction. The bananas undergo an accelerated respiration explosion, producing heavy volumes of carbon dioxide. If this extreme carbon dioxide accumulation remains unchecked in the sealed room, it will suffocate the fruit and permanently halt color development. To stabilize the crop, massive industrial fans are activated to forcefully extract the suffocating carbon dioxide, immediately replacing it with fresh oxygen. During venting, fans run for 45 minutes, crushing CO2 levels below 5%. A pressure gauge holds steady at 0.20 inches of water, ensuring uniform airflow. Instantly following extraction, a severe thermal shock rapidly plummets the ambient temperature from 75 down to 57 degrees. This violent sequence of high-heat chemical flooding, rapid gas extraction, and immediate thermal shock arrests internal degradation while locking in the fruit's perfect exterior color. What is the physical, measurable result of subjecting an entire harvest to this aggressive, high-temperature shock? This data table compares a conventionally ripened control banana against the experimental patented banana, with both evaluated at color stage 6. Direct your attention to the Brix column, which measures the fruit's soluble solids and total sugar content. The high-temperature engineered banana reaches a massive 23.3% Brix level, compared to the standard control's 20.3%. That represents a 15 to 25% jump in internal Brix value. But the most revealing metric is the firmness data, completely dispelling the industry fear that high heat produces a mushy product. The engineered banana retains an incredible 232 grams of physical resistance, heavily outperforming the control banana's fragile 174 grams. This chemical shift translates directly to the consumer's palate. The engineered fruit is significantly sweeter than those produced by standard ripening protocols. This increased cellular firmness means the much sweeter fruit is vastly more resistant to bruising during that critical final mile of retail transport. Through precise thermodynamic manipulation, post-harvest logistics actively re-engineers a crop's final cellular state.